All right, hi everyone. Welcome to another one of our WRRC spring seminar sessions. This is another presentation in our Red Hill theme. This week is Roger Brewer, and he will be talking about total petroleum hydrocarbons and the assessment of petroleum risk this week. And so let's introduce our speaker. Dr. Roger Brewer is a senior environmental scientist with the Hawaii Department of Health. His environmental experience includes regulatory compliance audits, characterization of contaminated soil, water, and air, contaminant fate and transport, vapor intrusion and human health, and ecological risk assessment. Roger's areas of focus include the chemistry and toxicity of petroleum fuels and improved methods for the collection of representative environmental samples. And so without further ado, Roger, please go ahead.
Hey, thanks a lot. And thanks for having me. This is a really interesting topic, something I've been working on personally since I got started in the environmental business almost 30 years ago now. There's still a lot to learn. So first I want to go over some terminology and that you're going to hear me discuss as we go through this presentation. First is BTEX, a lot of acronyms in this business. So BTEX is benzene, toluene, ethylbenzene, xylenes, plus or minus, might see an M, naphthalene, or methyl naphthalenes. pH is polyaromatic hydrocarbons. Mostly we look at naphthalene, things like benzoate, pyrene. TPH, hear us talk about quite a bit, stands for total petroleum hydrocarbon. This is everything else that's in a petroleum mixture. So petroleum is a mixture of hundreds of compounds. We have a few individual ones we look at. The rest we refer to collectively as TPH. And for now, under Hawaii's guidance, this includes hydrocarbon-related degradation compounds. In our upcoming guidance, we're probably going to adopt some of my colleagues in California EPA, where I used to work, have started using. Instead of TPH, they refer to HOPs, or Hydrocarbon Oxidation Products. These are usually biological related metabolites of hydrocarbons. That's a big issue for contaminated groundwater, especially. Then you heard me talk about action levels. These are concentrations of a contaminant in a media at or below which no adverse health or other environmental impacts are anticipated. Above an action level, it's a concentration in the media, of course. It doesn't necessarily mean you have a problem, it just means you need to look at it in more detail. We also refer to these as screening levels. Then risk driver, something especially when I think about today, we're talking about what's driving risk, TPH, compounds, or BTEX. The risk driver is a compound or compounds in the mixture that poses the greatest risk to human health and the environment. In other words, if all the other compounds, say BTEX and such, were below target risk levels or below action levels, this other compound, maybe TPH or something, could still be above action levels, still pose a risk. So we refer to it as a risk driver. A few misconceptions to talk about. See, the first is that TPH is only useful as a screening tool. It's a qualitative screening tool. So that's not quite true. So TPH and hydrocarbon-related degradation compounds often dominate contamination. And we'll see this later on in the presentation. They have to be quantitatively evaluated as part of the environmental hazard evaluation, or what is also referred to as a risk assessment. So we might agree on that, but some people would say, well, the methods aren't available to quantitatively assess risk posed by TPH compounds, this other mixture. But that was actually something we were working on when I first got started in the 1990s. So you can evaluate TPH as a mixture quantitatively in the same manner as we do individual compounds like BTEX and pHs. Another misconception, TPH only needs to be considered if benzene and other individually targeted compounds are not detected. That's not true. And again, something else we'll talk about is that the TPH component of petroleum can still pose a risk even when the concentration of BTEX and pHs or other individual compounds meet the target risk or action or screening levels. And then last, something we have discussions about, do we really need action levels? Can't we make everything site-specific, come up with site-specific detailed chemistry of petroleum and such? But that may be work for a few sites, but there are hundreds of thousands of petroleum release sites in the US, and definitely not that many of us regulators. So we really need conservative but reasonable, rational screening levels to screen out low-risk sites so we can focus on the high-risk sites. some references to look at. See, first, it's a document, risk-based screening levels. Sorry, I can't see my slides. Risk-based TPH action levels or screening levels, depending on whose document you're looking at. It's very similar to California environmental screening levels, which is something that I worked on when I worked for California EPA. Our last edition published in 2017. These are action levels for air, soil, and water. And there's also we published in 2018 a series of TPH risk case studies. It's referenced in the ITRC's document on how to assess TPH risk. We did it independently and published this through our office. And then a few papers on the reports we did on chemistry and toxicity of petroleum vapors. I'll mention later on. In 2012, we did a detailed field study of chemistry and toxicity of TPH and petroleum vapors from sites around Hawaii. And we published a paper on that in 2014. Some other references, I'm not going to go through all these. So several entities have published summaries of the toxicity of TPH. So you can see these in the slides later on when you get a copy. Down at the bottom, ITRC in 2018 published a document that some of us were part of that team on how to assess TPH risk in petroleum contamination. That's kind of the background. Quick, here's an outline. So I want to go over a lot of topics today. I'm just going to give us a few details on each topic. First, I want to go over just basics of an environmental hazard evaluation, what can be referred to as environmental risk assessment. I don't really like the term risk assessment because when we discuss that, some people focus entirely on the toxicity or toxicologists who may not know the other issues we look at. Then we'll look at what is petroleum made of and what is TPH and how are toxicity and risk evaluated and associated with TPH. Also, how do individual TPH components partition when released to the environment. And then what drives risk? The topic we're especially focusing on today is that TPH, or these hops degradation compounds, or BTEX, when you're dealing with petroleum contamination, especially in something like groundwater, or it could be in soil or air also. Then how are TPH and hops tested for? We'll end with that. So a quick schematic of potential environmental concerns posed by contaminated soil and groundwater, really for anything, including for TPH. So for contaminated soil, we might look at a direct exposure, say of kids playing in contaminated dirt, or adults, or ecotoxicity. Another big issue is leaching of contaminants and contamination of deeper groundwater. Also vapor intrusion into indoor air. For contaminated groundwater, we're often concerned about impacts to drinking water wells, drinking water supplies, but also, especially here in Hawaii and coastal areas or areas along rivers and lakes, is discharge into aquatic habitats. May not be a source of drinking water, but could severely impact aquatic habitats. And then the last one, number 7, gross contamination, which could be free product and sheens and such on water, or vapors, or I've got another slide I'll show you in a minute on other examples of gross contamination. So we know all these different environmental hazards, things we want to screen for up front at most of the contaminated sites we address. And to develop action levels or screening levels or assess risks, and there's a few basic things we need. First, we need toxicity factors for the compounds of interest. We need physiochemical constants like solubility, sorption, and its volatility and such. Then exposure assumptions, how long are the kids or adults being exposed to the dirt, how many years and days per year and such, how much dirt are they eating, how much air are they breathing, or water are they drinking, then some basic soil and groundwater properties. And then we can plug that into separate models and approaches for assessment of risk or for development of action levels. It'd be separate models for direct exposure, vapor intrusion, leaching, gross contamination. This is just an example of some action levels in our guidance for benzene in particular. So you see these 4 media: soil, soil gas, indoor air, and groundwater. And using these different models and these toxicity factors and physiochemical constants and such, we can derive screening levels. These are intended to be safe levels of benzene in all these different media. So in this case, if you look at benzene in soil, we talk about driving risk in terms of compound, but also in terms of potential environmental concerns. So for benzene contaminated soil, leaching to groundwater is the lowest action level. It's 0.3 milligrams per kilogram. And it's the lowest action level of all the other potential environmental concerns. So we can say if you have benzene contaminated soil, your main concern could be leaching to groundwater. Or if you take care, clean up the site to address leaching to groundwater, you should be addressing all these other concerns as well. Something similar for contaminated groundwater. See the different action levels for different environmental concerns. For drinking water, the action level is 5 micrograms per liter. That's the lowest action level of all the ones listed. So we say, in this case, if it's a source of drinking water, then drinking water toxicity poses the highest risk. And if you clean up the groundwater to address drinking water toxicity, you'll address all these other concerns. One thing you can drink benzene, the safe level for benzene in drinking water is 5 micrograms per liter, but you can't really start tasting it until 170 micrograms per liter. So that has important implications that you could be drinking benzene contaminated groundwater without knowing it. So a lot of what we do comes down to toxicity factors for individual compounds. So one point I always want to make is that everything is toxic at some dose or some potential. So water is toxic. A few gallons per day is a safe dose. If you want to think of that for water. If you drink more than a few gallons at one time, you could suffer from acute hyponatremia, which would essentially kill you. Aspirin, more toxic than water. So if you look at mini tabs in the grocery store or something, they're 81 milligrams per day, and that's considered a safe dose for aspirin. Anything above that on a daily basis could pose potential gastrointestinal, sorry about misspelling there, effects. Barium is a little bit more toxic than aspirin, 3 milligrams per day. It's considered the safe dose for young children. It's equal to about 2 small grains of sand per day of pure barium. And then there's multiple non-cancer related health effects. Arsenic's more toxic than barium, 0.0045 milligrams per day. That's about 1 millimeter grain every 2 years, just a tiny amount. This is 10,000 times below an acute toxicity level. That gives you an idea of how toxicity works. Then looking at an example like silver, or how you take this to develop screening levels. Real simple one, silver, the maximum daily dose for a 15 kilogram child on average, say 0 to 6 years old, 75 micrograms per day. We assume children drink 0.78 liters per day of water. That's EPA guidance. So 75 divided by micrograms per day divided by 0.78 liters per day comes out to 96 micrograms per liter, if I did that right, of silver. It's an action level. That's the key point I want to make here then, is dose makes the poison. You always hear toxicologists talk about this, or risk assessors. So you can have something that has a very high toxicity, like in this case, benzene. It's a high toxicity, but a very low dose. And the risk posed by that would be fairly low. Or you could have something a lot less toxic like barium, but a high dose of barium, even though it's low toxicity, could pose a high risk. So we would say that is what is driving health risk. That comes into play when we're looking at TPH versus BTEX as risk drivers and what's most concerned in water. There's more information on environmental hazards, or environmental hazard evaluation, and a series of training webinars we posted in 2017. The first 5 parts are on how to collect a good sample. That's really the biggest problem in environmental work, is getting a good sample to begin with, something that's representative, the question being asked. And then part 6, we talk about once you get reliable data, then what do you do with it? Here's the web page for our webinars. So let's skip on to what's petroleum made of. So you might be familiar with these. It's not this typical, it's a gas chromatogram for analyzing petroleum. This is a chromatogram of gasoline. So when you see a lot of spikes and such over on the left side, as you're viewing this of a gas chromatogram, those are the more volatile compounds. And the C here stands for the number of carbon molecules in each compound. So 8, benzene has 6, and then you see C8, C12, and such. Anything less than C12 is considered volatile. Maybe some of the C12 is compounds up to 16 carbon molecules are considered semi-volatile. Now for gasoline, you see, it's just an example from some California guidance. 23% in this particular guidance of gasoline fuel is made up of BTEX, and a tiny bit of naphthalene. 77% is made up of all this other stuff we lump together as TPH. So that's the big question. What's this other stuff? How do we assess the toxicity of it? That's gasoline. Here's kerosene. This is an example using JP5 fuel. So here you see, so there's gasoline, everything's on the left. Kerosene now, it's a small hump right in the middle. So it's kind of straddling this volatile, the middle of the volatile range here. And in this case now, for this particular sample, 89% of the sample, this fuel was TPH, is non-BTEX, non-pH contaminants. The total BTEX, I think in this example, was 11%. This turns out to be fairly old information for kerosene. Some of the more modern kerosene we've seen current doesn't have any BTEX or very minimal levels in it. So that's jet fuel, mostly this other stuff, TPH. Here's diesel. Now we've really spread out the chromatogram, including a lot more chemicals, compounds in it. And it goes all the way from the volatile range, but there's not much of it. Most of it's up in the semi-volatile to non-volatile, very low volatility range. And now 99% of what's in the fuel is TPH. It's this other stuff that we have to think about. We can't just look at BTEX, especially when you start looking at middle distillate fuels like this. So what is this other stuff? This TPH, something I've been thinking about for way too long. This is my last job as a consultant. It was in a large Western state, which I won't name. That red circle is me staring at this fireball coming out from this remote control backhoe. This was a gasoline station site that had been cleaned up. All the gasoline contaminated stuff they thought was dug up 20 years ago, and they're putting in an underground parking garage. I was, at that time, I'm a geologist, but I also do risk assessment. I was reading the risk assessment document in my office. It was a nothing site, and the guy I worked with calls up and said the site's on fire. Well, how can that be? It passed a risk assessment. It's approved by the state regulators, but they only looked at BTEX, and especially benzene and such. And there wasn't anything in the soil vapors. Well, if they tested the soil vapors, which I didn't know at the time, for TPH, all these other compounds, they would have realized they had flammable levels of gasoline vapors in the soil. So it's a good example of how you can't just look at BTEX. When laboratories report TPH, and it's something we'll discuss later on also. One issue is when they start looking at what is TPH, the laboratories have to run 3 different tests. And they'll, depending on how volatile the compounds are, they're trying to analyze in the mixture. So they refer to this as gasoline range compounds, diesel range compounds, and residual range compounds. Or you could call it TPH gasoline, TPH diesel, TPH oil. But this causes some problems when we get data back from the laboratory. You're going to get 3 numbers, but what we have to do, because it's all one mixture, is add up all 3 of those numbers, and that gives us a total TPH. And you can subtract individual compounds as needed. So keep that in mind. So we know what's petroleum made of now in general. It's mostly this stuff that this TPH is not BTEX. So and how do you look at BTEX and assess toxicity? I mean, TPH assess the toxicity and risk. And also what happens to these TPH components when released to the environment. Let's look at that next. So this was a group that got together in the 1990s, just right when I was starting. I was involved on the side. It's called the Total Petroleum Hydrocarbon Criteria Working Group. They published a series of documents on how to assess TPH. What is TPH made of? What's the toxicity? How do you use this in a risk assessment? A lot of people were involved in this. A lot of experts from oil companies, also risk assessors and experts from the U.S. Department of Defense and Navy, Army, Air Force, and such. And then several states, including our office at the time. Massachusetts was well ahead of everyone else, and also Washington and California eventually published guidance and such on how to assess TPH in risk assessment. The main thing they did is they took this mixture of TPH and divided it up into 2 separate groups of compounds: the aromatic compounds made up of benzene rings, and then everything else, which referred to as aliphatics. And they assigned toxicity factors to the group of compounds within a narrow range that had similar toxicity and similar physiochemical constants and fate and transport constant or factors. So you can see here, like for aromatics, they're divided into 2 separate groups from it's called equivalent carbon 8 carbons to 10 carbons, and then greater than 10 carbons to 22 carbons, all the compounds that fall in those 2 ranges. Then for aliphatics, they broke it into 4 different ranges from 5 to 8 carbons, 8 to 12, greater than 8 to 12, and then greater than 12 to 18. So you can subdivide into a lot more groups than this, but in terms of toxicity, especially these main 6 groupings, you can do a lot with for assessing TPH. And there's a lot of information on effective carbon, how you, this whole approach in detail in the TPH criteria working group documents. So now when they had each one of these different carbon ranges for aliphatics and aromatics, then the group went through and assigned representative molecular weights, vapor pressures, solubilities, Henry's constant, sorption coefficients, and all these physiochemical constants that you could use then to do modeling and assess risk. You see for each one of these groups. They also assigned toxicity factors to each of the groups. Some of the groups they put together. So really, there's 4 main groups. We follow Massachusetts guidance here. The C5 to C8 aliphatics compounds, just an example, oral reference dose, inhalation reference concentration. And you see the 2 other groupings for aliphatics. So the lower the number, the more toxic it is. So the C8, C18 aliphatics are more toxic than these lighter range volatile things. That's why diesel tends to be more toxic than gasoline when you're just looking at TPH, because it has all these heavier aliphatics in it. And then the really heavy stuff, greater than 18 carbons and higher, not that toxic. Here you're getting into motor oil and waxes and such. It's not volatile. Then you have the C8 aromatics, which fall in between the lighter range aliphatics and aromatics. So we have toxicity factors now, in addition to physiochemical constants for each one of these carbon ranges. Right away, just in terms of what happens to this stuff when petroleum in general, when it gets released in the environment, if you look at just the Henry's constants, especially, you notice the aliphatics, that if the number is above 1, it means that these compounds prefer to be in the air, not in water. It's just the ratio of the concentration in gas over the concentration in water. So if it's greater than 1, most of it's going to be in the air. So aliphatics prefer to be in the vapors. If you look at the Henry's constants for the aromatic compounds, including BTEX, then they're all less than 1. So aromatics prefer to be in the water. So that gives us some hint then initially at what we're looking at. And you can look at it this way. Here I've broken up, say, released a different type of fuel to the environment. So if you collected vapor samples above gasoline, kerosene, diesel, whatever, then you'll find mostly TPH in the vapor samples that you collect. And most of that stuff will be aliphatics. It's actually from some field work that we did several years ago. If you look in the groundwater, what's in the groundwater, that's where all the aromatics are going to go when they get leached out of the fuel. When the fuel hits the groundwater, the aromatics will dissolve and go into the groundwater. So you'll see a lot of BTEX, especially associated with the gasoline. With kerosene, you may or may not see BTEX, and same with diesel, but not it's in the fuel. If not, then you'll see a lot of these other aromatics, C8 and higher aromatics dissolved into the water associated with kerosene and diesel. So we think about what happened at Red Hill. It was jet fuel, which turns out not to have had much BTEX in it. Most of what was dissolved in the groundwater there, just from this simple approach, we know were aromatics, probably non-specific aromatics. There's no BTEX, and that's jet fuel, we don't think. So that tells us now a lot about risk. So we can look at this in more detail and look at what the carbon range makeup of this TPH mixture is in vapors, in the fuel, and dissolved in water. So we did a field study several years ago. I mentioned before, we collected vapor samples above, most of them age sites, and some fresh samples of gasoline, kerosene, JP8, and diesel. And most of the vapors are made up of C5 to C8 aliphatics. And there's some BTEX mixed in with that for gasoline, not so much. But it depends on the fuel actually for kerosene and diesel. But this is the TPH makeup of these fuels in vapors. In the fuels, here I just have the original carbon range makeup of the fuels. So you see for gasoline, most of gasoline in terms of TPH, excluding the BTEX now, is C5, C8 aliphatics, just a little bit of higher range aliphatics, C8, C18, and then a little bit of the other aromatics greater than C8 aromatics. You see when you get to kerosene, you're losing all this lighter range, more volatile stuff. They use JP5 on aircraft carriers, as you might know. And there, they don't want it to be that volatile, but it has to be able to push a plane. So most of what JP5 is made of is these C8, C18 aliphatics, and then greater than C8 aromatics. The pie chart I have here is an older formulation. This, in the current JP5 fuels, it's probably no green. There's not really much C5, C8 aliphatics anymore. Diesel fuel, at least from what we've heard in literature, doesn't have any C5, C8 aliphatics, which is odd because when we collect vapor samples above diesel fuel in the field, we see a lot of C5, C8 aliphatics. So something's missing there. These are all measured and such. We want to do the same thing with water. What's the TPH makeup of dissolved phase petroleum and water? So we spent 2 years and quite a bit of your federal tax dollars doing laboratory studies where we took we took different types of fuel, gasoline, diesel, and JP5, JP8, and we put a layer of the fuel on top of water, let it sit for 20 days, and then we tested the water to see what the BTEXN pH content was, but also we wanted to see what the aliphatic aromatic makeup was of what dissolved in the water. So we can get very detailed breakdown of that. And then we can assess the toxicity directly of the dissolved phase TPH compounds in water. But that didn't work. We tried several times, but labs couldn't reliably separate aliphatic and aromatic carbons dissolved in the water. It's something we're still working on research-wise. We couldn't do that, so we had to model it instead. So down at the bottom here, and actually some oil company, some chemists told me modeling is probably more accurate anyway, try to estimate what the TPH makeup is. So for gasoline, what you'd expect to be dissolved in the water when you have gasoline floating on groundwater would be mostly C5, C8 aliphatics. They're highly volatile, but they're also highly soluble, and they also make up a big portion of it. It's not a big surprise. Anything else dissolved in the water in terms of the TPH would be these other aromatics. It's aromatics are more especially soluble. Things like kerosene and diesel, most of what dissolves in the water, we can model this, would be the C8 and higher aromatic compounds. If there's any BTEX in the original fuel, you might see some of that, or the lower range, sorry, not BTEX, I mean C5, C8 aliphatics, you might see it dissolved in the water also. So now we know what the carbon range makeup is, and the vapor is fuel and dissolved in the water. So you think the next step is we could just develop action levels for each one of these carbon ranges, and then just go out in the field and test those the same way we do BTEX. That's not really practical because first it's just the cost of doing this in laboratories, and very few laboratories can actually run the carbon range analyses. And then also, especially with respect to water, then you have degraded mixtures. So that getting the carbon range data wouldn't be very useful. So all the degraded stuff would just come out as TPH. So an alternative, an alternative, which I don't have the numbers in here, but would be to develop carbon range weighted TPH action levels for specific types of fuels. So, sorry, I meant to have the numbers in here, I don't, but just say an example for TPH gasoline, we could, because we know the carbon range makeup of gasoline vapors, we can calculate action levels for indoor air, and then for soil gas, we know what the carbon range makeup of this fuel is, so we can calculate action levels for TPH, for vapor intrusion, and for direct exposure in soil. Actually, vapor intrusion, we probably use soil gas. And then for drinking water, if we know what the carbon range makeup is of dissolved phase TPH in water, then we can calculate risk-based action levels, again, for drinking water. So the idea here is instead of calculating or coming up with action levels for individual carbon ranges, is to calculate weighted toxicity of all these different carbon ranges that make up the TPH. This is similar to calculating the calories in a cookie. So you might know the individual calorie counts for individual ingredients of cookies, whether it's flour, eggs, or chocolate or something. So you could test, if you had a cookie in front of you, you could test individual, what's the concentration of chocolate, the concentration of flour and such. But an easy way to do it, if you know the general makeup of the cookie, then you can calculate a weighted toxicity just based on the calories in each individual ingredient. There's no need to test for individual components. You would just calculate a weighted calorie toxicity, if you want to call it that. And the highest, you know what the weighted toxicity is not going to be any higher than the calories in the chocolate, if you assume they're have the highest calories, and it's not going to be any lower than the calories in the flour. So there's a very tight range in reality of toxicities for mixtures based on the ingredients. We do the same thing for looking at fresh or degraded petroleum or TPH. The toxicity of the mixture can't be any less than the least toxic compound in that mixture, and it can't be any greater than the highest toxicity compound in that mixture. So in terms of TPH, can't be any less than C5, C8 aliphatics, or say the C8 and higher aliphatics. Can't be greater than that. So I know I skipped through that quite fast, but basically you can calculate these weighted toxicity factors. We discussed the general approach in our 2017 guidance and then our updated tap water approach. It's in the memo we published just a few months or in February. So it goes through how to calculate weighted toxicity factors for TPH mixtures for different types of fuels, especially with respect to tap water. And here's an example of just calculated weighted toxicity factors based on the carbon range makeup. So again, based on measurements in the field and the fuel, we know the carbon range makeup of TPH in vapors for gasoline, kerosene, diesel, and such in general. You could do this site specific, or we have some default values. Once we have the toxicity factors, we can calculate risk-based air screening levels or action levels for TPH associated with different types of fuels. We do the same thing for dissolved in tap water or in water. If we know that the general carbon range makeup, we can calculate weighted toxicity factors, and then we can calculate action levels for each one of these different types of fuels for the TPH in general. And then in the field, we just test the sample for TPH and compare that to an action level. Oh, so here it is. Here's the example for a TPH for middle distillates, the MD. So these are carbon range weighted action levels for TPH diesel fuel. So you see all the pink is for human health, green ecotoxicity, usually for terrestrial at site specific, and gray is gross contamination. So now we can treat TPH in terms of middle distillate fuels just like we would benzene and such. We go out and test samples in the field. We have action levels for those. So the last things I want to talk about then is what drives risk. Is it TPH or hops? So just to recount real quickly, we went over just in general what environmental hazard evaluation basics are. What do we look for in the field? Different environmental concerns. It could be more than just toxicity. What's petroleum made of? And we know that fuels in general are dominated by non-BTEX compounds, all this TPH stuff. And we looked at what is TPH made of, how are toxicity and risk evaluated. So we have 6 or more basic carbon range groupings of aliphatic and aromatic compounds that we can split TPH into. And we know they differ for different types of fuel. And we can look at how these different carbon range compounds partition in the environment. And then we can estimate weighted toxicities for this carbon range mixture in air or vapors over fuel or dissolved into water or for the original fuel itself. And once we do this now, we can develop risk-based action levels and then treat TPH in the same way we do as benzene and other compounds and assess risk in the field. So now what drives risk? TPH, or is it hops, these degraded compounds, or BTEX? Let's look at that real quick. So here are our current carbon range weighted TPH action levels for soil. So our action level for benzene in soil. So you have a gas station site that gasoline was released into the soil and you test it. You would test for BTEX and other compounds. We have action levels for those. The action level for benzene in soil is 0.3 milligrams per kilogram. We also have risk-based action levels for gasoline, kerosene, we just call it middle distillates, but this would be the example for kerosene, and then for diesel fuels. Actually, sorry, that's a mistake in this slide. It should say TPH is diesel fuels, and the last one should say it's residual fuels, heavy oil. So it's the TPH values. And the main point here is they're way above the value for benzene. So you would think benzene would be the main thing of concern. But actually, when you go out to gasoline station sites and such and test the soil, you may or may not find much benzene left in the soil. So TPH may or may not, or benzene may not drive risk. So as far as TPH versus BTEX is the fuel risk driver, when you're looking at soil for gasoline, if probably a lot of sites, benzene does drive cleanup at sites, gasoline contaminated sites. So if you clean up the site to address benzene, you're going to take care of all your problems. That's if you're using a 10 to the minus 6 risk, 1 in a million cancer risk for benzene. If you use, say, a 10 to the minus 5th risk, 1 in 100,000 cancer risk for benzene, your benzene action level goes up tenfold. In this case, you may not have a problem with benzene at the site because you still have a lot of other stuff left in sight, like the flaming pit example I showed you. Same thing for kerosene. The modern formulations, there's really no BTEX in it. So in that case, anytime you have a kerosene release, you're not going to find much BTEX or pHs in the soil. So all your risk and cleanup are going to be driven by TPH, not BTEX. Same thing for diesel. And again, the reason this happens is that even if there were trace levels of benzene in the soil, the dose is so low that the risk is going to be pretty low, even though the toxicity of benzene is pretty high. And even though the toxicity of these TPH compounds in comparison is relatively low, the dose is so high, or the concentration in soil is so high, that it's going to be the risk driver, not benzene, or not BTEX. And looking at air, we've done quite a bit of work looking at the TPH and carbon range compounds in air. Here are action levels for benzene in air is 0.36 micrograms per cubic meter. It's probably below background for most urban areas. Then the screening levels for, gasolines, kerosenes, and diesel are, you see a lot higher. So what, 1,000 times higher or something. So you would think, again, maybe benzene is the main thing we need to worry about when we're looking at impacts to air or vapors coming off of fuel releases. In reality, what we see, same thing from fresh fuels, we tested vapors above gasoline, diesel, and JP8, and there was actually high benzene in the fuel, in the vapors from diesel and JP8. So there is some BTEX in there that is going into there. We were surprised at that. So maybe in that case, benzene does drive the risk if it's very fresh fuels, but if you back off to a 10 to the minus 5 risk, say for benzene, then your TPH is probably going to be driving risk. In reality, even for contaminated air, give me the TPH data, we can make a good call on it without even looking at the BTEX data. What's the problem? When we look at field studies and we get soil vapor samples from sites all around Hawaii, we don't see that much BTEX in the vapors, even at gasoline sites, in comparison to all these aliphatics and stuff. The aliphatics tend to drive risk. So again, what drives risk in terms of, for indoor air, most of the time it's the TPH, and it's these light range, mid-range aliphatics, not the benzene. Then for tap water, and this of course is a big issue recently. Here's our action level for benzene in tap water, 5 micrograms per liter. And again, the TPH, a lot less toxic, maybe 50 or more times less toxic. And the action levels are equivalently much higher. So again, you might think, well, benzene is our main concern at the site. When we go out and actually look at data in the field, maybe at gasoline sites, especially when it's fresh and the plumes are still volatile, then you do see a lot of benzene in the water and BTEX, and that's going to be driving risk at those sites. For kerosene, diesel releases, depends on the formulation of the fuel, but especially for more modern formulations of kerosene and diesel, you're not going to see much BTEX in the groundwater or in the water, period. It's going to be mostly these other aromatics and such. And so the TPH component's driving risk, not the BTEX. So that's the fresh stuff. How about for petroleum contaminated groundwater? It's degraded, and most sites we look at, the petroleum is heavily degraded. So if you went out and tested for BTEX, if you went out and tested for individual carbon ranges in the water, you wouldn't find anything. It's just a lot of degradation, partially oxidized compounds. So that, in this case, we need to look at the weighted toxicity of not just the TPH, the carbon ranges, but also the combined, these carbon ranges and BTEX, the mixture as a whole. What's the weighted toxicity of that? And this we do in the same manner. If we know the proportions of individual carbon ranges that make up the TPH and the proportions of the BTEX and pH compounds that make up the BTEX component dissolved in water, then just like the chocolate chip cookie, we can calculate a weighted toxicity factor for that mixture in total. And then we can calculate a weighted toxicity factor for degraded petroleum associated with these different fuel types, gasoline, JP5, or diesel fuel. That's a big thing we're looking at now and recently, really for quite a while. Some people have been looking at this for the last 20 or 30 years. So it's a chemistry and toxicity of degraded petroleum in water. So take your BTEX and TPH, degrade both of them, they turn into hydrocarbon oxidation products, HOPs, as the Californians call them. It's just a combination of these acids, esters, alcohols, ketones, and phenols. There's a lot of research published on the toxicity of individual compounds in these mixtures. And when the laboratory tests your water sample now, they're just going to report it in the absence of silica gel cleanup, which pulls out all the polar stuff. So you don't clean up the sample. In the lab will report this still as TPH. And in this case, it's representing all the degradation compounds. It's not a very good lab test. It's not very precise, but right now it's the best we have. And we can argue quite a bit. I do quite a bit with my friends in the oil companies and other such about the chemistry and toxicity of this. There's a quote from Aristotle. At some point, there's such a tight range of what the weighted toxicity could be. It's like calories in the cookies between the chocolate and the flour. It's like Aristotle's quote here. It's the mark of an instructed mind to rest easy with the level of precision that the decision requires, not to try an exactness that is unnecessary for the problem. So we don't really need to get detailed information on what specific compounds degradation products are. We can estimate based on the original mixture of what the weighted toxicity would be. At least it's a starting point, which is good enough for most sites. So here's some examples, screening levels, where we calculated weight toxicity of carbon range plus BTEX. This is the HOPS action levels in our upcoming guidance. And again, benzene, I just threw this in here for comparison. Again, 5 microns per liter. One thing with the TPH action level, let me skip back real quick. It was originally 390, 339, 211, and 189, these action levels for gasoline, kerosene, and diesel. When you degrade the stuff, the benzene action level goes from 339 or whatever it was, it actually falls down to 190. That's because we're including degraded benzene in the mixture now. So the mixture is actually more toxic, the TPH, because all the benzene is included in your TPH measurement now. For kerosene and diesel, the risk-based action levels for tap water actually go up a little bit because we're including all these low toxicity degraded xylenes in the water and calculating the weighted toxicity. So in terms of TPH versus BTEX for contaminated drinking water, I know that was a lot of details to go through, but get the general idea, I hope. But say if you have a fresh spill of gasoline that already has a lot of BTEX in it, then yeah, BTEX is probably going to drive your risk. Don't even bother testing for TPH if it's fresh. Test the BTEX. If you clean up the water to meet BTEX action levels, then you're done. Not very many fresh plumes out there that you'll see. For kerosene, it depends on the formulation. For more modern formulations of kerosene and diesel, again, there's no BTEX, very little BTEX in the fuels. So you have to test for TPH. And TPH is what's driving risk, not the BTEX. For degraded plumes, of course, now all these compounds are oxidized. So your benzene's oxidized. If you test for benzene in the water, you're not going to find the degradation products. It's just going to come out lumped in with your TPH. So for degraded plumes, the TPH, or in this case, HOPS, we'll call it that, are always going to be driving risk, not benzene. So the last slide I have is how are TPH and HOPS tested for. And this really, that's where we are now. So we've gotten back, we have a much better idea, at least a starting point on how to calculate, assess the toxicity of these mixtures of fresh and degraded petroleum compounds. One point again to make is TPH action levels we publish, they apply to the total concentration of TPH related compounds in the mixture. So you have to add in these separate ranges that the laboratory reports. Ideally, the laboratory would just report a single concentration for both TPH or hops if they're looking for degraded compounds. And that's what gets compared to the action level we have. So we have action levels right now for gasolines, middle distillates, heavy fuels. So you test the groundwater, you get a total TPH number from the lab, and you compare it to the appropriate fuel type that was released there. So site-specific carbon range data and action levels, they can be useful for vapor intrusion investigations because the vapors above different fuel types really vary, especially from middle distillates we saw in the field. So that would be useful. For degraded or old sites, it's not really useful. For cases like Red Hill, it is useful to try to get site-specific carbon range data for the fuel itself, and then we can get a better idea of what went into the groundwater. We're working on that now. All in all, we definitely still need better test methods now that we know what to do with the TPH for both TPH and for these degraded compounds. So I know that's a lot of information, a lot of different points, but just a quick summary to get back to the main points. No BTEX, no pHs doesn't mean no risk. And methods are available to assess the risk posed by TPH compounds, the non-BTEX pH stuff. TPH always needs to be considered in any petroleum release site, even if benzene and other compounds are detected. A lot of times it's going to drive risk, not these individual compounds, as we said here. Even when the other compounds meet their action levels, especially benzene. So if you look at Red Hill, there's no benzene in the groundwater there. There's no benzene intentionally in JP5 jet fuel. So of course, if you just look at benzene, like my flaming pit example, it's going to pass a risk assessment. You have to look at the TPH component, all the dissolved other hydrocarbons and related degradation products. We definitely need better test methods, both TPH and hops. There's people working on that. And then the carbon range data, specific action levels, site-specific, this issue came up. They're mainly useful for testing parent fuels associated with large fresh releases, whether it's crude oil or jet fuel or gasoline or something, and for testing of indoor air and soil gas. Otherwise, these default makeups that we use are good enough for most sites, default compositions and action levels associated with it. And the site-specific action levels, they're allowed, but they're going to fall within a pretty tight range. We already know what the range would be for an individual site, unless someone wants to argue about the individual original makeup and the toxicity of degradation compounds and such. So that was it. Any questions, comments, and ideas? If anyone who's new to this totally understood everything I just went over, then come talk to us. We'd love to hire you. It's kind of like looking at a car. The individual pieces and parts aren't that complicated, but when it's all put together, you just look under the hood, it can look kind of complicated. But when you dig into it, it's not that difficult. And the whole issue with TPH, like this quote from Neil deGrasse Tyson, is we never really knew what to ask for early on. Now we're starting to understand it more. We have really for the last 20, 30 years, but getting better. And now we know what questions to ask, so we can start looking at better ways to assess things. So with that, then I'll take any questions. And you have my email, so I'd love to chat about stuff like this, not improve our guidance also.
Great, thank you so much. That was a really excellent talk. I learned a lot. So we'll open the floor to questions. So the audience is free to either type your question into the chat and we'll read the question to Roger, or you can raise your hand and then I'll give you unmute permissions and you can ask your question. So please go ahead. Okay, so we have one already from Michael. So thank you for a thorough review. Are action levels regarding toxicity based on individual compounds, or are they based on potential cumulative effects?
That's a good point. For the action levels, of course, for BTEX and such are based on individual compounds. But what we often do for individual compounds is we set our target risk really low, as if we assume there's 3 or 4 or 5 other compounds there that have the same health risk. So they do address cumulative risk of individual compounds. For TPH, because it makes up such an overwhelming mass of what's in the air or the soil or the water, then we don't address cumulative risk for the other individual compounds. They're assessed separately. So TPH action levels assume cumulative risk of all the compounds, hundreds included under TPH and hops.
Okay, another chat question from Kristen. Can you share documents capturing the diesel impacts with high benzene in the overlying vapor?
Yeah, that's in a paper we published in 2014, and the report's 2012. So if you send an email, then I'll send you the paper and the report. Otherwise, they're posted to our EAL, Environmental Action Level webpage. So some links there. That was a surprise, all the benzene in water, and of course, in the vapors. And of course, the first thing the geologists, the field people do is blame the laboratory. That they screwed up the analysis, but we actually sent 3 separate samples of vapors from diesel fuel to laboratories, and they all came back with similar levels of benzene.
Okay, chat question from Aurora. Given aliphatics want to be in vapor and many households smelling and experiencing headaches, did DOH do any vapor testing? Any idea of the TPH components that could have been producing those effects?
Well, if you look at the memo we published in February, then I think in there we estimated the carbon range makeup of what would have gone into the air from the dissolved phase mixture. So we know it would have been mostly the C8 and higher aliphatics from kerosene. So we have a pretty good idea of that. The original fuel formulation we got from the Navy suggested there were pretty high levels of xylenes and maybe toluene in the water, but it turned out when they're testing the fuel itself, as preliminary data, we don't really see that much in there. So it'd been mostly these mid-range aliphatic compounds. You know, one thing about the vapors too, I'll point out, in the fresh samples we test over gasoline, diesel, we find a lot of BTEX, which is surprising for diesel. But when we go to the field and we collect soil vapor samples in the field, we find very little BTEX, even at gasoline station sites. And that's a surprise, because that's what you think would be driving risk for vapors at gasoline station sites. But you just don't see much. It's mostly these lighter range aliphatic compounds. So the theory is that the aliphatic compounds, they go into vapors along with the aromatics. They go into the vapors when the gasoline percolates down into the soil, but they quickly dissolve into water in the soil, and the soil moisture get kind of extracted from the vapors, and you're just left with a lot of the aliphatics.
Okay, another chat question from Kristen. Why do you include organic acids in the total petroleum hydrocarbon analysis?
Let's see, let me skip back to that. Here it is. So this, if you look at our 2018 document up here, this is our risk-based or our case studies of TPH risk we published. So it's a attachment 5 to that document talks about the chemistry of degraded petroleum, and there's a geochemist I've known for quite a while, Dawn Zemo. She published a paper in 2016. There are a few others on the basic chemical makeup of degraded petroleum, dissolved phase petroleum associated with middle distillates. And she broke it into these 4 groups here. They actually assigned toxicity factors for each one of these groups, which we discuss in the paper we published, and calculated weighted toxicity, including the acids. And it's based on what they published in their paper, the initial degradation products, as we hypothesized before, have a very similar toxicity to the original compounds that were dissolved in the water.
Okay, we still have some time for questions. Is there anyone else? Barbara Beacons put a comment in the chat. One possible reason for seeing benzene and lighter aliphatics over diesel may be biodegradation. And there's a link to a paper for people to reference.
Okay, we don't really see a benzene at degraded sites. We only saw benzene for diesel fuel with the fresh samples we were getting from the local gas station.
Rob Schofield said, did you say you assume benzene is present in degraded middle distillates for purposes of assigning the toxicity factor to middle distillate TPH?
Let's see, did we? if it was in this, just get back to here, if it was in the original fuel formulation, and we use California Luft manual from 2015, they had a carbon range, a breakdown of for diesel fuel and gasoline. And for the diesel fuel, they had some BTEX. No, actually, I think they did. Yeah, in their water. So we would have used that in our weighted toxicity. Here, if you see under diesel here in this slide for soil, this is the last pie in that column, soil under diesel. It's mostly TPH, but that thin blue sliver is the BTEX component. Now in naphthalene, that was in the California Luft manual as the default for the makeup of diesel fuel. But actually, in the groundwater itself, yeah. So in our default toxicity factor for the groundwater itself, we did include BTEX when you run the calculations for effective solubility as part of the, we're calculating weighted toxicity for degraded mixtures, total TPH and BTEX. I forget the exact percentage.
Okay, had a question from Tao Yan. Are there literatures that verified the assumption that hops have the same toxicity profiles as original petroleum compounds? Could they be more toxic if the generation processes generate metabolites as aldehydes or ketones?
You know, that's the big debate, the discussion. And you know, originally TPH was just ignored. And a lot of states still ignore TPH. You know, this mixture of degraded non-BTEX compounds in groundwater. So some states, they specifically just ignore it. So we wouldn't think it is. So what was the question again?
So are there literatures that verified the assumption that hops have the same toxicity profiles as original petroleum compounds?
Yes. So that one, you know, some of the literature is going to say it's not toxic at all. And of course, that's not true because water's toxic itself. So right now, the literature out there, this Zemo et al. Paper from 2016 is one of the more useful papers I think has been published. And they look at 4 stages of degradation. And as it gets more and more degraded by their take, it becomes less and less toxic, you know, only by a factor of 4. So even the heavily degraded stuff, they would still say is still toxic. So could it be more toxic? Well, I know some risk assessors have argued that, but for the mixture as a whole, which is what we're interested in, we know some individual compounds might be more toxic, but what we really want to know is for the mixture as a whole, what's the toxicity? And I haven't seen any detailed studies that go into depth more than the Dawn Zemo's paper. And even in her paper, she didn't calculate a weighted toxicity. We had to do that in our 2018 document that I have noted here. So if you happen to know of any, definitely we should chat about it. Try to track those down.
There's a question from Kyle Kajihiro, but first, Kristen Bruce put a quote from Don Zemo. Just connecting that. Our work demonstrates that the metabolites identified in groundwater at biodegrading fuel release sites are in classes ranked as low toxicity to humans and are not expected to pose significant risk to human health. That was from September 2016 Integrated Environmental Assessment.
Right. Yep. That's the case. You know, a lot of the cases when you have contaminated groundwater degraded, for one thing, it's going to degrade faster than it migrates away from the source area. You know, Red Hill was obviously an exception to it. So they're low toxicity. Nobody would argue with that, these TPH components. But so it all comes down to what the dose is. So it may be low toxicity, but low toxicity doesn't necessarily mean low risk. It's something you have to think about on individual sites. So definitely the action levels related are going to be, you know, much higher than they would be for individual compounds like benzene or when you're looking at chlorinated solvents.
Okay, so Kyle's question was, where can we find the list of fuels used in Red Hill and the description of their components and their degradation products?
Yeah, so right now, the data we have, information we have is they were mostly storing JP5 at Red Hill, jet fuel. And I think there are maybe a few other fuel types they stored there in the past. So we know the basic makeup of JP5 jet fuel. You can find that on the internet. But what we need to do to assess risk, and I thought this might come up, but sorry, down here, is we need more detailed data than what you find generally published. So here's my wish list, say for Red Hill. If you're assessing the risk posed by the fuel itself, say, drinking the fuel itself, or contaminated soil, which we assume most of the petroleum is going to be the pure fuel, then you need a lot of data. You need your standard BTEX. What's the composition in terms of your BTEX, naphthalene? You could add in some other components as needed, but especially the carbon range information. Each one of these carbon ranges I have listed here has a different solubility, especially in maybe volatility. So to understand the fate and transport of fuel when it's released, you need a pretty extensive breakdown of the aliphatic and aromatic carbon ranges. There's only one laboratory, Newfields, that I know of that can give us this kind of breakdown. And we're actually sending samples to that laboratory to test and get a breakdown of this detail for a JP5 jet fuel from Red Hill. Once we do that, we can get a much better idea of what the dissolved phase TPH look like at Red Hill in the groundwater. And then based on that, we can estimate a much more accurate weighted toxicity. It's not going to be that different. It would just be a little bit more accurate. If we're just concerned about toxicity of water, of contaminated water and vapors, we're mostly interested in just toxicity. So we don't need as detailed of a breakdown of aliphatic and aromatic compounds. We just go back to these. There's really just 4 different groupings of aliphatics and aromatics with different toxicity factors. We can get away with just those for the water. For vapors, all we need from a laboratory testing is, a breakdown of these 2 different ranges of aliphatic compounds and just 1 of the aromatics, because there's just the 3 that are volatile. So that's what we'd like, the data we want to get for Red Hill. We have it partial. We have enough data to look at, the water in terms of toxicity, except we don't have a good breakdown of the aromatics to look at what the concentration might have been dissolved in the water at Red Hill.
I have another question from Aurora. What do we know about fuel additives beyond what is captured by TPH that might have strong biological effects with respect to Red Hill?
And if you mean in terms of biological effects, in terms of ecotoxicity or humans, or
human health.
Okay, yeah, that's a good question. That's something we looked into early on, is trying to get more detailed information on the additives that were in the fuel. And all we had was just published information at the time of other additives that could be in the fuel. And one of the main issues that came up was antifreeze. It's this fuel system ice inhibitor that could be that are actually in the fuel there in Red Hill. And that stuff is fairly soluble. So that's another thing that would likely have dissolved into the water and been a part of the mixture in the groundwater.
Can I ask a follow-up then?
Yeah.
Okay, so was that analyzed for at all? I'm assuming that was the glycols?
Yeah.
Glycol ethers?
Yeah. So it was, I think they did find low levels of it in the Red Hill shaft, but I haven't seen the data for it.
Thank you.
Okay, do we have any other questions?
Okay, I have one more then while we're at that. And I can turn on my video. Thanks so much. I guess one of the things I've learned is that there was likely mobilization of sort of earlier contamination with the slug sort of dropped into Red Hill shaft. What do we know about what's about those? I mean, I guess it would be classed under the additives and the other stuff, because previous, whatever was sitting in there before from earlier releases.
Oh, from earlier releases. Well, presumably it was JP5 from earlier releases or some kind of jet fuel or kerosene. So anything, as it goes down, percolates through the beta zone, then you're going to lose the more volatile stuff. So your lighter range aliphatics are going to be coming out of the fuel. And then when it gets to groundwater, the aromatics are going to go into the groundwater, the lighter range aromatics. So we know that would have been mostly C8 and higher aromatics, because based on the new preliminary data we have, there's not much xylenes and other stuff in the jet fuel there. So we have a pretty good handle on what would have dissolved into the water and what would have gone into the air. And what would have been left in the fuel would just been degraded. First, it would, the volatile stuff would have come out and then it would have degraded in place some. So you would have some of the degradation products potentially leaching out of the fuel, hung up in the rocks, getting down into the groundwater.
Sorry, one more and I'll let somebody else go, but has DOH, I guess, assessed not only just the fuel that released, but what was in the shaft, and then post-chlorination, would there be any interactions with the chlorination steps or treatment steps along the distribution lines that could help explain what was being experienced by households?
Yeah, I know that some groups were looking at that. I think Diana Felton was more involved in me than looking at that in the system. I didn't look at that in detail yet. It's a good question. Really, in the end, one question is what was coming out of the taps. So based on the formulation of the jet fuel itself, JP5, then we can make a pretty good guess of what was dissolved in the water. And if there's any free product, we know that also in terms of just the hydrocarbons. But then what was the other stuff? There could have been some of the fuel system ICE inhibitor compounds in there, and then other products produced as it went through chlorination. I know people are looking into that. Be a good research project.
Okay, I had a question from Ernest Lau. Are you researching and identifying the range of fuels that have been stored in the Red Hill facility over its 79 years?
Yeah, I know our office is looking at that in probably the underground tanks group. I haven't looked at it myself in particular. We know in general what they were. I mean, they're petroleum fuels, probably mostly jet fuel, kerosenes and such.
From Catherine Wrong, there are some concerns over the use of simple green in cleaning, which affects the solubility of hydrocarbons in the water. Would this affect the action level?
That's a good question. Something and as people in our office looked into initially, so we think simple green may have been used in cleaning up the shafts so it was spilled. So it would have enhanced maybe it might have enhanced the solubility, but it would have broken up the fuel and carried it down into groundwater much faster. But yeah, the effects of simple green with that is another useful, interesting study we look into, and the toxicity of simple green itself. But you see there's a lot of emulsification of the fuel in the water in the shaft. And that was one thought some people had, was that was because of the simple green emulsifying the fuel. It basically would mobilize it and get it down to groundwater faster and carry it maybe through the system.
Referring back to Ernie Lau's question and earlier question by Kyle Kajihiro about what fuels were stored at the site. In the tour in December, as if I recall correctly, there's currently, in addition to JP5, there's also diesel stored at the facility. And I do recall two main fuel lines going down the lower tunnel. One was for JP5 and one, I believe the other one was for diesel.
Yeah, and I think that if you think about that in terms of the carbon range makeup, diesel it's a wider spread, but ultimately the toxicity of dissolved phase JP5 and diesel would be fairly similar. You're still looking at the C8 and higher aromatic compounds in general. Just the concentration might be higher for, I would guess it would be a little higher for kerosene than it would for diesel that you would see in the water. But again, something we haven't looked at in detail. So what I want to do, and we're talking to the lab, is get more detailed carbon range breakdown of these fuels, since we were unsuccessful in physical laboratory experiments to get a better idea of what the chemistry would be in the dissolved phase hydrocarbons in kerosenes versus diesel. Ultimately, I think it'll come down to the concentration more than the toxicity. It'd be similar. Somebody asked about Simple Green. I actually contacted the company that makes Simple Green. They're real friendly. They actually have detailed chromatograms for some of their Simple Green products, and with marker compounds, if you're looking, because they use it for testing, for cleaning food equipment. So people go in to test the equipment or test the food. They actually have chromatograms for key markers in Simple Green to look for when you're testing food to see if any Simple Green got in the fuel. So if anybody's interested in that information, then send an email.
Catherine Wrong says, what method does Newfield use for determining the carbon ranges?
I have an idea, but I won't even attempt to try to explain it. So I can put you in touch with them in general, but I don't have a strong background in lab chemistry, especially the analytical methods themselves. But the person that they work with, there's another laboratory in Massachusetts, Alpha Laboratory, and there's a guy there, Jim. Sorry, Jim, if you're listening in, I always forget your last name. Starts with a no, and it's Italian. But he actually wrote some of the original laboratory methods for Massachusetts back in the 1990s on how to break down the TPH component into aliphatics versus aromatics in dissolved phase samples, water samples. But with that breakdown, it only gives you a small breakdown of aliphatics and aromatics. And to get deeper into it, to break it down even more ranges, to get more detailed idea of it, then Newfield's a group there, Eric, I think it's Leidman, developed the methods to do that. They're the only laboratory I know of in the US that can do it. Get this carbon range breakdown, which is another reason why we need TPH, weighted screening levels instead of individual carbon range screening levels. But if you're interested, I can put you in touch with them. I'd love to try the experiments again, like I showed before with the glass jars with fuel on top of water. But that's the only laboratory I know of that I would spend another 25 or 50,000 of your tax dollars attempting to run these experiments on. But the other labs, since there's some chemists listening in, they initially thought they had separated the aliphatics and aromatics in the water samples, but when we looked at the gas chromatograms that were supposed to be just aliphatics, then you could see spikes of aromatics all through it. So they weren't able to successfully separate the aliphatics and aromatic compounds in their analysis.
Patrick Casey asks, are there records of AVGAS historically stored in the Red Hill tanks?
So I've heard of Avgas being stored there, which is aviation gasoline. I forget the exact details. It's basically, as I understand it, a mixture of gasoline and kerosene. So I've definitely heard of it. So what would happen if Avgas hit the groundwater? What would dissolve into the groundwater? You'd expect to see it. It would look something like a mix of jet kerosene and gasoline. So you'd see more, maybe C5, C8 aliphatics dissolved into the water initially. And you'd also, I assume there's BTEX in it. You'd see that dissolve in the water along with the aromatics. Maybe if there were any heavy aromatics, you'd see some of that in there. So the toxicity would be somewhere between, the weighted toxicity of that mixture would be somewhere between gasoline and kerosene.
Aurora, since you're a host, do you want to just ask your question?
Okay. Sorry, thanks. I guess I was interested in your sort of professional opinion on what you see as a priority for monitoring as the defueling gets carried out at Red Hill, because I understand the risk for releases is highest during fuel movement. And I guess priorities, I mean, what do we need to be measuring? Where do they need to be? Do the measurements need to be made, and how frequently, in order to not have to have a much more, I guess, rapid response or to prevent what recently happened. And then as a follow-up, how do we most effectively monitor the plume from what's already happened? So it's sort of two questions there. What do we need to be monitoring, where, and how frequently?
Yeah, and I think, what do we need to be monitoring? As far as where, is they're installing a lot more monitoring wells around Red Hill. And that's been one of the issues in the past. And with the Navy also, is them just getting money to install these monitoring wells. They're not cheap. Environmental programs tend to be poorly funded to begin with. But now they have plenty of money to put in more monitoring wells around Red Hill. So we're going to learn quite a bit for that. So you can put in the monitoring wells, and they're vapor probes underneath the tanks themselves. And that's the way you initially catch a release, is from the vapors. And and they're already doing this. You don't just test for BTEX, obviously, especially with jet fuel. You test for the TPH and everything. But what to monitor in addition to what they're not doing now, I'm not really sure. The main thing was to put in more wells. You just want to monitor the pipes themselves, the system itself, as you're defueling, just to avoid any releases. So you're not monitoring after the fact. And then what else should we be monitoring for in the water? Not sure. We need more information on the additives, what's in the fuel. That's one thing that's been missing. And what happens to these additives, say the ice inhibitors, once they get in the groundwater.
Okay. Thanks. And I guess I suppose the monitoring wells that are being installed wouldn't have prevented detection before, given this release sort of went straight from the lines into the shaft. So is there better monitoring, I guess, in place within the facility itself that you're aware of?
Yeah, that I'm not sure of. I'm sure they're going to be watching it extremely closely as they defuel these tanks. And how are they going to defuel them? Maybe it's like a gas station. You don't necessarily pump all the fuel out into another tank. Maybe they just use it up. I'm not sure what their plan is and how much of the fuel they use. Maybe it's part of defueling. They're just not going to refuel the tanks as they use the fuel in it instead of trying to ship it somewhere else. I don't know the details of that.
Thank you.
We have a question from Michael Fry. Do commercial under the sink water filters remove TPH and BTEX?
Yeah, they should. If it's carbon, if it's a activated carbon filter, it should remove the TPH and BTEX, and it should pull out the degraded compounds also. They can be polar, but again, I don't know as much about that. I can definitely look into it to see what type of filters are most useful. That's what in the laboratory they remove the degraded compounds by running the water through silica gel. That absorbs all the polar degradation compounds, which is why we don't want them to use that when they're testing water samples, because we'll miss all the degraded compounds. I know people, again, I have lots of contacts. So I have some contacts with some people who market and manufacture water filters. I can put people in touch with if they're interested. Thanks also, everyone.
Roger, thank you very much for that really important and interesting presentation. Gets us all thinking a little more and understanding the framework for understanding possible human health impacts of this contamination. So really big thanks to you and the work you're doing for this presentation and for the work you're doing.